So this is the same equation that I showed in the previous slide, and this can be used to plot the speed torque characteristics. So essentially drawing TEM versus omega r, and the slip is actually, the slip and omega are dependent, so you can write the whole expression in terms of omega r or in terms of s. So that leaves the unknowns as the rotor current IR, and usually VR prime is also, when drawing the speed torque characteristics, we will draw for different values of this VR. So that can be considered as a known quantity. So then the question is, given all the other conditions, how do you calculate this IR prime? So you can calculate that fairly simply from this equivalent circuit referred to the status site. So one method is to calculate the Thevenin voltage at this point, looking into this part of the network. Okay, so that would be the voltage appearing across the magnetizing inductance, and the impedance would be the parallel combination as shown here. Z theta is the parallel combination of the magnetizing reactance and RS plus the leakage reactance. Okay? And the Thevenin voltage would be the voltage division. So that's this impedance divided by the sum of all the impedances times Vs is VTH. So if you know the VTH and the series impedance ZTH, then IR prime is given by this VTH phasor minus the applied rotor side converter voltage, which is VR prime over S, divided by all the impedances, starting with ZTH, then the rotor leakage impedance, and the RR prime over S. These were combined as RR prime over S. So once we calculate IR prime, this is all in a like you can write a MATLAB or a MathCAD script and draw the speed torque characteristics from that. So I'm going to give an example. So this is the parameters of a 1.5 megawatt DFIG based wind generator system. Grid voltage 570 volts, 575 volts RMS, 60 hertz. All the 5 impedances include the magnetizing inductance. Those are all given, and the number of poles P in this machine is 6. Okay? So that's going to decide what is the synchronous frequency for the applied 60 hertz grid frequency. So we are going to draw the speed torque characteristics for 3 very different values of the rotor converter voltage VR. For VR of 0, which is essentially like operation as a squirrel cage induction motor, the rotor is short circuited, or an application of 0.03 per unit at the rotor side converter terminals, or negative 0.03 per unit, meaning it is out of phase with the stator voltage. Okay. So these are the corresponding speed torque characteristics at the 3 different applied rotor voltages. So let's initially look at VR equals 0. As I said, that is the squirrel cage uncontrolled or shorted rotor winding case, and that gives you the plot in the middle, the red plot. That is the well-known speed torque characteristics of an induction machine. So for positive slip, so that is from S equals 0 at this point. So the x-axis is the rotor speed omega m in radians per second, and S equals 0 corresponds to synchronous speed of operation, and that is equal to 60 hertz. 2 by 60 is 377 divided by the number of pole pairs, which is 6 poles, 3 pole pairs. So 377 over 3 is this number, 125.67. That is the synchronous speed. Any speed less than that, you are operating in the subsynchronous mode or positive slip, and any speed higher than this, you are operating with the negative slip or corresponding to the supersynchronous mode of operation. So positive slip corresponds to, and positive slip with 0 rotor side converter voltage corresponds to the conventional induction machine operating as a motor. So that is the well-known speed torque characteristics for an induction machine. So this is the peak torque, this is the kind of the linear portion, and this is the starting torque, and so on. Now, the squirrel gauge motor can also be run as a generator, as long as you're able to rotate it at a speed higher than the synchronous speed or negative slip, and the corresponding speed torque characteristics are given in this part of the plot. Now, the application of the rotor side voltages and therefore the rotor side currents significantly changes these speed torque characteristics. So, for example, when you apply VR of minus 0.03 per unit, meaning it's going to be out of phase, but again low values of low magnitudes, then the resulting speed torque characteristics are given by this dotted brown curve. And the last, probably the more interesting case, is when VR is in phase and again at the same magnitude 0.03 per unit. That results in this blue speed torque characteristics. Why it is special is it shows that for this type of VR, this type of phase relationship, even at these positive S, the subsynchronous mode of operation, the torque is actually negative. So negative torque, positive speed corresponds to negative power, or actually in our motor convention, it is really power being generated, electric power being generated by the DFIG machine. Okay. So that clearly shows that even when the speed is actually less than the synchronous speed, power generation is possible with the DFIG. But not for any positive slip value. It is only this very narrow range it is able to generate power, but this corresponds to VR of 0.03 per unit. If you can change that, then you can extend this region over which we have generation in a subsynchronous mode of operation.